Oh, shoot. Okay. Let me check something. All right. Fluffy. Okay, welcome back. Actually, let me share. Uh, let's let's do some kernel dev before sleep. Applications. All right, let me share this on my Instagram. Okay, let me check my YouTube. Not sure. No one's watching right now. It's okay. Okay, let's share this to Instagram. Okay, so welcome to our stream. Tonight we're gonna make some applications. All right. So the application will be running on the operating system, of course. Nope. Sorry. So, all right. So let's follow this page here. So we're almost done, actually. We are at section 12. So we have like 5 sections left. We'll be done in no time, actually. So let's do micro. So in this chapter, we'll prepare the first application executable to run on our kernel. Let's go! Okay. Memory layout. In the previous chapter, we implemented isolated virtual space address spaces using the paging mechanism. Let's consider where to place the application in the address space. Right. So, So here we're trying to put our application, right, somewhere, and the address space is basically the memory, right? So we're gonna define a specific region of memory where we're gonna put our application. So here it seems like we'll be creating our own another linker script for the applications. So user.lt. By the way, oh, there's no one watching. It's fine. Okay, so here we're gonna start with our user LD linker. All right, so entry, this is gonna be the entry point, and then we're gonna define sections as usual. Okay, so dot equals 0x1. How many zeros is that? That's 6 zeros. 1, 2, 3, 4, 5, 6. Okay, and then this will be the machine code. So dot text keep what's this? Okay, dot text dot start, which is basically we're doing this again. So here, see that? We're doing this again. So it's the ELF header. Sorry, the ELF file format. You know. Okay, so start. This is gonna be this text section, and this one text dot. This is very similar to the kernel linker that we had earlier. Okay. So this is gonna be the read-only data. So RO data. Well, the name is self-explanatory, isn't it? And then align it to 4 bytes. Well, align to 4 kilobytes. Yeah, whatever. I forgot. Dot read-only data. Dot read-only data. Dot everything. So okay. And then we do dot data align 4 as usual. Actually, let's look at what align 4 is for. Actually, let me check the kernel linker if I did the. Oh, I did use this similar syntax. Okay. Okay. So here, this is the data with initial value. So it's gonna be this section over here. This one. This is the section that we're writing. So this would be dot data dot data dot. There we go. And then finally we have the BSS. Okay, data that should be 0 filled at start. Okay. Okay. Usual. Boop. SBSS dot SBSS. Boop. Then dot equals align. Okay, 16. Yep. And then we increment add itself by this number, which is 16 kilobytes. No, sorry, 64 kilobytes. And then we set the stack top to dot. Okay, and then we assert. I'm not sure what assert is. I think there's a. Oh, if the executable too large executable. Okay, so it looks pretty much the same as the kernel's linker script, isn't it? The key difference is the base address. So this is the base address right here, right? So that the application doesn't overlap with the kernel's address space. Assert, yeah, it's talking about this part, is an assertion which aborts the linker if the condition in the first argument is not met. Here it ensures that the end of the .bss section, which is where is the .bss? Here. This is much better. Much better. See that? This one. It ensures at the end of the .bss section, which is the end of the application memory, does not exceed 0x1800000. This is to ensure that the executable file doesn't accidentally become too large. Okay, simple, right? Just checking in case, like making sure that the executable is not larger than the available memory. Yeah. Simple. Okay, so let's create a new file. Okay, called user.c. Now we're on the user land. Let's go. So this is the user space. All right. I am absolutely confused on what I'm doing. Well, not really confused. I'm just very exciting. Okay. So let's do include user.h. All right. We'll write the header file later, and then external character stack top external char. There you go. And okay. So next we'll set a attribute. Okay. To the compiler. We're telling the compiler, I guess. Attribute. Did I spell it properly? Attribute. Yes. No return. So there'll be no return. Void exit void. This is a function. So for this is an infinite loop essentially. Okay, so this is an infinite loop. Infinite loop. Duh. And then put character. This is the put character to the screen function, and we'll put this as to do. Okay, we'll do this later. Next, we set this part, so attribute. So this will be the section, which is .text.start. Lost one here. Okay. Whoa. All right. Okay. Next, this one will be okay. Attribute naked. So don't compile any extra shit. And then void. This is the starting function. Inline assembly as usual. Volatile. Yep. Okay. So move. Yes, this is the move instruction. Okay. So another RISC-V thing. Alright, so if we check RISC-V assembly cheat sheet here, alright, we're moving where's the yes. Oh, actually this is a copy. Copy the stack top to the SP or the stack pointer. We're copying this. We're basically setting the stack pointer. Okay, and then we're gonna call. This is. I think we're calling a function. So calling. Okay. This one. Okay. Backslash n as usual. Right. then call exit. There we go. Okay. So we're calling the functions exit and main. So we'll eventually have a main function. Okay. Here, the execution of the application. Okay, this is. Oh no, it's not done yet. So stack top R top done. Okay, and then we have semicolon. So the execution of the application starts from the start function. Execution of application starts here. The start function. Okay. Check kernel boot process. Okay. Prepare the exit. Okay. So it sets up the stack pointer. Yes. Here. Calls the app main function. Okay. And then we prepare for terminating app. However, for now, we'll just perform an infinite loop. Okay. Also, we define the put character function that the printf function in comma.c refers to. We'll implement this later. Unlike the kernel initialization process, we don't clear the .bss section with zeros. This is because the kernel guarantees that it has already filled with zeros in the allocations function. So, we difference diff from kernel init process. We do not clear .bss section 0. BC kernel make sure of setting to 0 with alloc pages function. Okay. Cool stuff, right? Hold on. Why did my camera look so weird? Hold on. Right. Next, so the allocated memory regions are only filled zeros in typical operating systems. So otherwise, the memory may contain sensitive information about the process. It could lead to creators. Yeah. That's correct. Lastly, prepare a header file. Yes, of course. So pragma once include common.h, so the common header files, attribute no return void exit. Okay, so this is like a define like a promise. We're gonna say, okay, we will define this function called exit, and then we'll promise you later to define it. I guess that's what who was it? T Coding. Sorry, he's a great guy, legendary guy. Okay, he does a lot of C stuff. I love him. He's one of my heroes. So, okay. So first application. Let's write a first application. So shell. Oh, it's a shell application. All right. So include user.h. Okay, main. So you see, right? This is the main function. Okay, so which the user.c will call. C inline assembly will call. Okay, so this one will make it an infinite loop. All right. Building the application. Applications will be built separately from the kernel. Let's create a new script. New script to build the application. All right. So, okay. Interesting. Run.sh. Oh. Alright. We're basically gonna edit the application here. Let me put that up and we'll use that for client. Okay, so this one, we'll set this one to the variables over here. Let me variables, that's for Kimu, it's for Mac. Obj copy is equals to LVM object copy. So this is a binary. All right. Okay. So this is, we're gonna put the flags there, and here. Via Ignatia. Okay, so let's build the shell, aka the app. Okay, so cc c flags wl, oh boy, passing the options to the linker, t user ld, which is the specify. Is it specify the linker script? Okay, and map. There shouldn't be a space here, isn't it? Okay, and then is equals to shell.map, output as shell.elf file, and then include shell.c, user.c, and common.c. And then we have an object copy set section flags, which will be the flags of BSS, which is allocation and contents. Big O binary shelf. Now into shell dot, supposed to be shell dot bin, and then object copy I binary. Oh, what is that? Little risk 5 shell dot bin dot o. Hello, one viewer who's watching. Okay, and then here you would add shell.bin.output. Okay, so let's see. The first cross-compiler call is very similar to the kernel build script. Compile C files and link them using the linkers. Okay, so this one is compile, okay, C files and link with user.ld linker script, and then converts first object copy command. Okay, this one will be converts the executable, converts the elf to raw binary format. Okay, and okay, raw. Okay, and so the raw binary format is the actual content that will be expanded in memory from base address, in this case 1 2 3 4 5 6. Okay, the OS can prepare the application in memory simply by copying the contents of the raw binary. OS copies content of raw bin. Common OSs use format like ELF where memory contents and their mapping information are separate. But in this book, we'll use the raw binary for simplicity. Okay, now obj copy here. Second obj copy command converts the raw binary execution image into a format that can be embedded in the C language. Okay, converts raw binary to format can be embedded in C. Let's take a look what's inside the llvm nm command. So llvm, oh, haven't run it yet. Here it is. The prefix underscore binary underscore is followed by the file name, that's correct, and then start, end, and size. These are symbols that indicate the beginning, end, and the size of the execution image, respectively. In practice, they are used as follows. External character, binary shell start, okay. Main void, shell bin, yep. Okay, so it's bracket, so they have an external character. Okay, so shell bin is equals to the bin start address. And then it prints out the size and prints out, okay. This program outputs this file size of shell.bin in the first size of its contents. In other words, you can treat start a variable as it contains the contents like shell.bin contents here. Binary shell.bin size variable contains the file size. However, it's used in an unusual way. JLVM again. Okay. Let's try running it first. What the stack protector? What did I do? Did I write properly actually? Show.map, show. What did I do? What did I do? What did I do? I thought it's correct, don't know. Did I write something wrong? User LD. Hold on, let me try copying this line. Maybe I wrote something wrong actually. Did I? Oh. Oh. Oops. Text. What the hell? Oh! I forgot a semicolon! Oh, jeez. What did I do? Oh, I forgot another semicolon, didn't I? Oh, boy. Oh, okay, it runs properly. That's good. Control AC, quit. Clear. Okay. Binary, boop, 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 boop. Okay, so here, it outputs it as llvm nm shell.bin.o. There it is. Okay. Program output size of shell.bin and first byte of its content. In other words, you can treat. Okay. Variables contains the file size. Okay. So if I do lvm_nm shell.bin.output, and then I grep the binary shell size, not shell bin size. Okay. So it says that. And okay. LSLAL. Okay, which is listing everything. Alright. Here, 66096. Okay. And then you use that to print. So this is a hexadecimal number. So if you do Python 3 and then you print this out. Oops, sorry. Oh! The first column outputs is the address of the symbol. This so this thing here this hexadecimal number matches the file size, but this is not a coincidence. Generally, the values of each address in .o file are determined by the linker. The A in the second column indicates the address, that the address is a simple absolute that should not be changed by the linker. That embeds the file size as an address. By defining it as an array of an arbitrary type, will be treated as a pointer storing its address. However, since we're embedding the file size address here, casting a result in the file size is a common trick or dirty hack that exploits the object file format. As we added shell-bin to Clang arguments in the kernel, compiling, it embeds the application executable into the kernel image. Cool. Cool. You see, if you go in the so this one, if you use this number and then you print out that hexadecimal number, that is the file size itself. Oh, cool. And oh yeah, we also added this to the kernel. Cool. And in this assembly, we can see that the text.start section is placed at the beginning of the executable file. The start function should be placed. Okay, let's see. LVM. Okay, we're gonna object dump this shit. Okay. Sorry. Oops. Oh, boom. Okay. If you go up, okay, over here. See? Look at that. Huh? See that? That is exactly where the start function should be. Alright. If you go back, sorry, where is it? User.lte. See that? That's the base address. That is exactly where it should be. Okay, and if you, oh well, actually, shell.c. Oop, micro user.c. See that? See that? That is exactly where it should be. Okay. Absolutely amazing. Okay. Absolutely genius. Okay. Mwah, amazing. Okay. See that? Oh wow! Look at that! Oh, look at that! Amazing! Just pure. No, it's not discombobulation. Pure majestic perfection. Okay, you see, this is the reason why I program. I don't program because I'm gonna make millions of money or millions of no. You see the fact that the start section is at that part. We tell the compiler, please put we tell the linker to put the start section at that memory address, and it does it for us. You see how amazing the compiler is? The compiler is heaven sent. All right, it's the most beautiful human invention since the 7 wonders of the world. This is the 8th wonder of the world. The C compiler is the 8th wonder of the world. And if you don't believe me, go write a compiler yourself and you'll realize, oh my god, that is absolutely discombobulating. Okay, anyway, I'm ranting now. So okay, we just did it. Application's done. Let me check user mode actually, if there's anything that's long. Yeah, it's already 22:52. So we'll probably end it here. Thank you so much. We'll git add everything first. Git commit. Edit application shell.c and modify the script to what do you call it? Compile the alpha. Sorry, the shell binary file. Alright, that shall be the end of the stream. So thank you so much for watching. I feel so happy seeing this. Absolute cinema. The absolute cinema, okay? Thank you. I'm gonna running out of energy. I'll go sleep. Alright, see you later guys.